will see this evening, today, to sensing, in particular for anything that has to do with low energy physics detectors, to quantum communications and more theoretical aspects, so direct simulations or even algorithms, quantum algorithms development. And the number of applications and initiatives within the community are starting to grow, so that just recently a quantum technology initiative has been approved and started at CERN, with the idea not only to coordinate all those activities that are happening in the different fields, but also to have a better, let's say, framework to build the collaborations with other communities and other actors in the quantum technology field. So I would like to also stress that we strongly believe that quantum computing will bring a big change in the computing landscape in the future. But in order to get there, we need to start learning how to use it. And now we need to start to understand now what are the challenges if we want to make it into practical applications, and how much, I would say, we should rethink the solution we use today in high energy physics in order to make those problems solvable with quantum computing. So the topic that I will discuss today is quantum machine learning. So some of it has already been introduced by Stefan in the previous session. So I only wanted to highlight a few points which I think are very relevant. It is true that there are many different approaches. Quantum machine learning is a lively field, and it's still something that is developing very quickly and evolving and changing over very quickly. I think we can safely say that in most cases, current applications rely on hybrid approaches. So again, variational approaches have been introduced before, and I will not go into the detail now, but they basically represent by far the preferred solution for most of quantum machine learning applications today, and this also applies to our studies. What's interesting about this from a machine learning perspective, so from someone that comes from the AI or classical AI world, and it's looking into the quantum computing, is really understanding how do we translate the basic concepts of machine learning into quantum. So how do we represent a learning rule? Is a pillar of machine learning, such as gradient-based optimization, still optimal in the quantum computing world? There seem to be, for example, hints about the fact that a well-known classical problem, which is represented by the presence of vanishing gradients, might be more important in the case of a quantum model for a large number of qubits. How do we address the problem of data loading? This is also something that was mentioned before. This is not at all something that should be neglected, not only from an advantage kind of measurement perspective, but also from a point of view of the model's performance. It could be that, we already know from the classical point of view that smart embedding of our input data can make much, let's say, can make the task of the machine learning model much easier. And as far as advantage is concerned, it's always the big question. As far as we are concerned, we're not looking into this in order to provide advantage. Advantage could be there in many, I mean, we can speculate among many different directions. This can come from computational advantage, from sampling, representational power, or sample size. We don't know yet at this time. We are not looking into quantum machine learning to prove advantage. In fact, so far, we are applying those techniques in problems, two problems that we know very well how to solve classically. So we are building use cases that we can solve, that we control entirely, and that we know very well how to manipulate. And in such a way, we intend to learn how to, what are the advantages and the disadvantages of trying to do this with quantum algorithms. So you see here a few examples. They cover most of the data processing chain in high energy physics. We go from Monte Carlo simulation to the reconstruction process, which is the process that analyzes the raw detector data and tries to reconstruct high-level physics quantities to the final steps of an analysis. For example, the classification of an interesting signal data with respect to background, which normally is much more abundant than the signal we are searching for. But also examples of workload optimization using reinforcement learning. This is something that is being applied to different problems, at the technological level, optimization of our accelerators, for example, accelerated complex, or of the computing infrastructure. So let me go through some of those examples, and I will start with quantum generative models. So those are models that we are investigating. Well, they're classical counterpart, at least, to start with. So we are investigating to replace Monte Carlo simulation. The problem with simulation is that while it is very accurate and it's essential to any experiment, it is also extremely intensive in terms of computing resources. So it's been already a few years that the community has been looking into alternatives, maybe methods that are not as accurate and precise as Monte Carlo simulations, but can be run and much faster. Now, generative models are particularly promising, and we've had a lot of research in the field. In particular, generative adversarial networks are among such models, among the most actually successful for this kind of applications. I don't want to give the details about this. We can discuss it later if you are particularly interested in those. The core of those kind of networks is the fact that the generator network, the one that we will use to sample our synthetic image, synthetic detector output, or synthetic particles, are trained using the feedback of another network. So this is not the typical supervised learning approach. Now, we started to look into how to use quantum circuits to reproduce generative models because we hope we might observe a larger representational powers thanks to a quantum representation of data and of the correlations among the data. Now, we performed investigations in different directions. In all cases, the first thing we had to do was to actually downsample our problem to a manageable number to a manageable dimension, something that we could easily map to a small number of qubits. And we have investigated different kinds of data representation and different kinds of quantum computing approach, both qubits approach, but also continuous variables that you could implement using photonics. But I will not talk about this today. So again, as it was mentioned, I think there was a question today about how to start with quantum machine learning, and the answer was look at the examples that already exist. This is what we did indeed. We did start by running the quantum GAN model that is available on Qiskit. And we quickly got very nice results. So what you see here is on the bottom right plot, you see how an electron entering a calorimeter volume would deposit its energy along the calorimeter depth. So it will travel to the detector, will deposit a certain quantity of energy along the way, and then we would register this in the different sensitive cells of the detector. Now we have extracted a one-dimensional energy profile, which is the blue histograms that you see there. And we have tried to reproduce this using a hybrid classical quantum GAN, in which the generator is purely quantum, and it's based on the architecture that you see below that was published. We used just 3 layers of Y rotation plus entanglement. And this generator, this quantum generator, is trained against a classical discriminator, which is implemented in PyTorch. And I would like to stress the difference in number of parameters between the generator and the discriminator. If you know a little bit about networks or generative adversarial networks, you would see that in most cases, you tend to have a balance between the generator and the discriminator, while in this case, we clearly have a very small generator that is capable of training against a much larger discriminator. We've applied this also to a 2-dimensional, so we increased the number of qubits. The 1-dimensional case was solved with just 3 qubits. We increased to 6. And we built a 2-dimensional image like the ones that you see on the side. In this case, basically, we reconstruct the energy depositions on a 2-dimensional plane. In this slide, I'm also showing you how the loss functions evolve through the epochs, just because I wanted to show you how stable the training actually is. So we're very happy with this result. Now, the problem is that this model is not a real generative model. Now, in which sense? This was a model that was meant to learn a hidden probability distribution from a data set and embed this in a quantum circuit. And it does this task, performs this task very, very well. It is, however, not suitable for sampling directly the specific single events. This is not something that it is just capable of generating an average event. So we started from these algorithms, and we built a collaboration with Cambridge Quantum Computing and decided to build a real event sampler. And so we designed a 2-step quantum generator that it's capable of learning the average distribution initially and then sample from it real images. And you can see, again, this is a hybrid approach that we put in place. You see at the bottom how the network performs on an average image, how we can generate specific specific particle samples. And again, you can also see that the training is indeed stable across the large number of epochs. This is still, however, work in progress. There are some things that we need to, some optimization that we want to do. In particular, at this level, with this model, we are still linking the number of images that we can generate to the number of qubits that we need to use, which is not exactly what we want to do over the long range. Let me move on to something else. You've probably already heard about this analysis. This is done in collaboration with the University of Wisconsin and IBM. Now, in particular, this was an application of a classifier, the likes you saw described by Stefan during the first session, to a Higgs boson identification problem. Now, you see on the top right corner how this problem is solved classically. Well, not how, but the classical result. What is it? What kind of data is it that we're looking at? Classically, the problem is solved by using a boosted decision tree that is trained on a few tens of input parameter features that describe the kinematics of the events or the topology of the events, and are used then to identify Higgs signals and separate those from background events, an interesting event. For the quantum implementation, again, the first step that was needed was really dimensionality reduction, which we did using principal component analysis to a different number of features. And the work then tested different configurations, so different input encoding, different entanglement, and also different SVM, quantum SVM approach. So a pure variational classifier and a kernel-based method, which I remind you, again, this was explained before, but the difference basically between the two methods is in the kernel methods, you are actually optimizing and training the first step in your quantum circuit, the one that is actually encoding the classical data into the higher dimensional space, quantum space. Now, here you see some results. These were presented in July at the ICHEP conference 2020 by the Wisconsin group, which compared the two approaches. You can see on the top line is the result of the variational classifier approach, and on the bottom you see the kernel method approach. Both are, so just a little bit of detail. So can you see my pointer? So this plot, the two here compare quantum simulation to, which are the dark curves, to classical approaches, basically a BDT and a similar SVM architecture that is trained classically. And you can see that in both cases, those are, the performances are very similar. On the right, there is a comparison between a quantum simulator and runs on real hardware. On the top cases, for the variational classifier, the code was run on a 20 qubit hardware, and on the bottom for the kernel method, the code was run on a 27 qubit on the 27 qubit hardware. In both cases, you can see that we approach the classical and quantum methods are very similar, and it's nice to see that the simulation, the quantum simulation, is capable of reproducing the quantum hardware performance behavior. Last example, last but not least, I mentioned the problem of reconstruction. So I mentioned the problem of extracting interesting physics quantities from the raw detector output. One of those, of the, let's say, major type of reconstruction problem that we need to solve is what we call tracking. So the reconstruction of particle trajectories from the raw detector digital output, which basically looks like something that you see here. A collision happens at the center of the detector, and then you see all your detector lighting up like a Christmas tree, and you need to try to disentangle all those different hits and trying to understand which one belong to interesting trajectories and which one are just combinatorial noise, or in any case not interesting events. Now this is a very complex and compute intense task. Since a few years also, in this case, deep neural networks have been studied in order to solve the problem. Different architecture, from convolutional neural network to recurrent networks to graph neural network. So far, graph neural network represents one of the best approaches. The idea here is that somehow we try to move away from the geometrical hierarchy of the representation of the problem, and we represent the detector output as graphs of connected hits, and use networks to do the classification. Now, of course, for a real, full-scale event, this would require, of course, very large graphs. We would be talking about embedding data in order 10 to the 5 nodes as typical graph size. Now, in this context, we decided to start a quantum investigation. Now, the HepTrack, the GNN, so the graph-based network that has been developed, is built as a cascade of network classifiers. There is an initial embedding network, the input network, that's encoding the detector output. And then there are 2 classifiers that are run iteratively, and that represent a classification on basically interesting hits and interesting segments between the hits. So the classical performances, the performance of the classical network is very high. You see a few figures reported here. We decided to start from this approach and replace each one of those components with a quantum variational circuit. Now, in particular, we decided to use 3 tensor networks. Now, those are hierarchical classifier. Those circuits, they're called hierarchical because you see that they maintain a specific structure in the way they are built. The idea is that they're usually 3 tensor network are usually built with parameterized circuit, are alternating rotations, for example, or other single qubit gates to entanglement gates, as you see here. And after each of those iterations, one of the qubits is measured, and the dimension of the network reduces along the depth. This basically means that whenever we want to add hidden dimension, we need to add additional qubits, and I will show it to you in a minute. Just let me explain how we apply this to a geometrical problem, such as nodes and the segments or hits and segments problem. So you see here how 2 hits on the two sensitive layers of the detector would look like, represented by their geometrical coordinates. So we directly use 3 qubits to represent those 3 geometrical coordinates, so that each one of those circuit is used to represent one node. There is an initial input encoding that is based on Y rotations, and then we have the real TTN circuit that you see here that is also built using RY rotations for a total of about 11 parameters. Now, as I mentioned before, if we want to increase the dimension of the network, we need to add additional qubits. You see how this is done in the case of the edge network, which needs to classify segments between 2 nodes and therefore encodes the nodes features as these 2 sets of 3 qubits, sorry, plus additional hidden features that are added like this, like additional qubits. The training, both networks are trained as I mentioned, as variational circuits. So the training loop works always in the standard way. We use a Adam classical optimizer. One thing that maybe it's worth mentioning for the node networks, because this shows also why this work still needs to work on some, to improve some optimization. And it's the fact that when we need to classify nodes, we need to classify a specific node with respect to the position of the other 2. This means that we need to be able to build a circuit for each one of the possible combination of nodes. And now you understand that if we have too many nodes, we cannot just let the number of qubits that we use explode. Right. So, but we set up this problem for a relatively simple detector with just a few layers and a relatively simple, small number of hits, and we build a quantum network with just one hidden dimension. So basically, exactly the circuit that you saw represented before. Now, in order, we assessed the performance of the networks. Those are the green curves that you see on these 2 plots. On the left side, you see the loss functions and the way it evolves through the training steps. And on the right side, you see the accuracy and the way it changes through the training steps. Now, in order to make some, to have some classical reference we could compare to, we also simplified classical networks with different number of hidden dimensions. And you can see how here, I don't know if you can read the slides, but we go from a dimension 1 to 10 to 100 when we move from the yellow to the blue to the red curve, which improves the performance of the network. You see it clearly here on the accuracy. At the same time, the comparison clearly show that a very relatively small quantum network really outperforms classical networks with a larger number of parameters. Now, of course, this has, we're not claiming any advantage here at this point, because we would have better methods to solve this problem classically, but the simple one-to-one comparison, I think, shows the potential for this quantum application. Before concluding, I just wanted to move away a little bit from high energy physics. I hope I didn't lose all of you, so maybe these last slides will capture back a little bit of the attention. So on the left, you see the problems that we've been trying to solve. But if you look at it, this looks very similar to how air traffic data would be recorded on the world scale. This is in particular is the number of airplane trajectories that were recorded on April 2019. So we decided to try and apply this same tracking problem to a problem that is more, you know, I would say not more important, but at least that have a very strong direct impact on everyday's life. Maybe not now that there is the COVID, but in the future. Why? Because improving air control and flights trajectories would have many different good, and would bring many advantages in terms of, you know, cost and efficiency, in terms of safety. For example, anomaly detections could be used to detect unusual behavior, or areas where unusual behavior is most likely to appear because of problems with weather, for example, or other things. Environmental aspects could be improved, reducing carbon footprints, or also improving safety by helping predicting emergency situations, for example. So we started a collaboration with about this topic, and we got access to specific data recorded from collision warning systems that basically track airplanes in a way that is very close to what we do in high energy physics. So for example, whenever we talk about a detector hit, we are basically, as far as planes are concerned, we are basically talking about the timestamp with associated position to it. When we talk about events ID in high energy physics, we are talking about a specific ID of an airplane transponder. Particle ID would be the flight type. When we talk about segments or edge, we would be talking about distance between two airplanes. And when we talk about a node, we would just be referring to an airplane in a specific position. So if we do a direct translation of this problem into the model that we have developed for physics, then we would have, for example, our node network that would look like this in terms of airplanes. And we have, you can see, I put it here a little as a little inset because it's very preliminary results, but this was also published, presented last July at the ICHEP 2020 conference. You can see here performance of the quantum architecture in terms of the area, the accuracy, the area under the curve. In particular, here you see two different versions of our quantum networks, in which the best one is basically involving using some input data embedding. That we have introduced during this that we are developing basically now. Okay, this is basically all I wanted to show you. I think I'm already over time or close. As a summary, I just wanted to say that we are very excited about opportunities in quantum computing and more in general quantum technologies at CERN. And in particular, the Quantum Technology Initiative has started recently. The idea is really to improve collaboration between among scientists in our community, but also between our community and external and other actors and experts in other fields. And one of the major focus, I want to stress it now again, is really the idea of developing skills and gathering expertise, even if quantum computing is not something that we might use daily right now. As far as quantum machine learning is concerned, I think the initial studies, those initial studies yield exciting results. For now, we are for now, all our studies are configured as exploratory studies. We are trying to use use cases that we know very well as the perfect playground to understand different quantum related aspects. And also, I would like to stress that besides the work on the Higgs identification problem that I mentioned, all other applications so far use noiseless simulation. So this is this discussion about realistic simulations and implementation on hardware is something that we will get to, but it's not, we're not there yet. So none of the results that I showed you beside Higgs was run on hardware. And I think that's all. Thank you.
Thank you, Sofia, for the very nice talk. Since we're already almost running out of time, maybe just one quick question. So how many qubits would you need to use quantum SVM for data classification in an experiment, for example, at the LHC or any other experiment at CERN?
Well, the examples that you saw use very few qubits. We are talking about, it depends how we configure the analysis. A realistic analysis could just use a few tens of qubits. We don't necessarily need to go to hundreds because we focus on specific analysis. We focus on data that has already gone through some sort of pre-processing and selection. Now there are other applications in our field that instead would require hundreds of qubits or even more. And I'm talking more about problems like the reconstruction kind of problems when we deal with the output of big detectors.
Okay, thank you again.
Sure.
So then let's continue with our next speaker. Our next speaker is Bob Coecke, who's going to talk about quantum natural language processing. I'll give you a very short introduction. Bob Coecke is professor of quantum foundations, logic, and structures at the University of Oxford, and he's senior scientific advisor for Cambridge Quantum Computing. At Oxford, he heads the multidisciplinary 50 members quantum group, and at CQC, he heads the 12 members Oxford-based CQC QNLP team. His pioneering research includes categorical quantum mechanics, compositional natural language meaning, and QNLP. He co-authored Picturing Quantum Processes, a book containing 5,000 pictures. He's a founding father of the quantum physics and logic and the applied category theory communities and the Diamond Open Access journal Compositionality. Thank you, Bob.
Thank you. Thank you. Hello. Let me share my screen. I will take this one. Is it shared?
Yes, it's all working. Thank you.
Okay. So we all go through quite a difficult time these days. We're all 6 months at home or something like that. And then you go a bit crazy. And among the things I did to deal with boredom is I built myself an IBM quantum computer, as you see on this picture. And I did stuff with it. Some quantum natural language processing. Well, I mean, this is not what I'm going to talk about, although this was a lot of fun. What I'm going to talk about now is what we actually really did. And this was not with the cardboard computer, but if you want to see the cardboard computer show, you can see some more lively shows than this slide talk. Here, this is on YouTube, and you can go to SamSpace, which was the conference it was at. If you want to see a more lively, detailed version of what I'm talking about here, you can also watch something on YouTube here. And then if you want to see a chat between me and Ilyas Khan, who's the CEO of Cambridge Quantum Computing, about the more big picture of what I'm talking about today, you can go there too. So this at CQC. Second one was an MIT seminar. So if you go to Google MIT tokens or something, you find this. Okay, let's start with the story of today. So around 2008, which is now already quite a while back. So at the University of Oxford, where I still am, there were 3 people. So one of them was this one, Marnoush Chadrazadeh, and she knew about something called categorical grammar. So what is categorical grammar? Categorical grammar is a sort of thing people would typically, to some extent, associate the name Chomsky with, although Chomsky had very particular rigid views on what this thing was supposed to be. But fundamentally, it's a piece of math that kind of tells us how grammar works. The way it works is essentially, if you got a sentence or something like that, you assign grammatical types, and each particular grammatical type corresponds to some element of a particular mathematical structure. And then if you put them together, then something happens. If your sentence is grammatically well typed, it all vanishes and it basically tells you, yes, this is a sentence now. So you see a little calculation here on the slide. That's how that stuff works. And it essentially, in mathematical terms, goes back to somebody called Lambek and pioneering work that was done in the 1950s even. So that's one big thing. And this sort of doesn't depend on languages and stuff like that. So this is really how we understand the mathematics of grammar already since a very long time. So I was talking about people who were at University of Oxford, actually in the same corridor, I should say, using the same printer room and kitchen and toilet. Somebody else who was there, he was Steve Clark, and he knew a lot about current modern NLP. Well, I mean, modern NLP now is actually still a bit different than modern NLP in 2008. But the basic idea is that meanings of things correspond to vectors in a vector space. The way you build them, it's at the time it was via co-occurrence. One counts how many times a word comes in the context of another word. Now, of course, it's all machine learning and which by means of which you establish vector embeddings. But essentially, you got all these vectors representing meanings. And then there was a third person who was myself. And I knew about categorical quantum mechanics. So categorical quantum mechanics, let me do full screen, that's probably better. Where's my full screen? Enter full screen. Categorical quantum mechanics is something you can find in this textbook, which was mentioned earlier, which contains 5,000 pictures, because it's basically quantum mechanics entirely in terms of pictures, not illustrative pictures, but pictures which are mathematical entities and which actually represent your usual vectors and Hilbert spaces and linear maps. So you can do that. I mean, that was something which was around. So one thing people now know in the quantum computing circles is maybe ZX calculus, because, for example, the ticket compiler was mentioned earlier, and what does the work to optimize circuits and things like that is in fact ZX calculus. And I know people at different companies are using ZX calculus for many different things like error correction and things like that. So it's kind of a practical workhorse coming out of these diagrammatic quantum mechanics, which is now practically used in practical quantum computing. And I'll actually use it later in the talk for something too, something very different than, say, quantum compiler optimization. But anyway, so we had categorical grammar. I'm just going to go back to these first two. We had modern NLP, and a question which people asked then was, how can we combine grammar and meaning? Because there is this old work by people like Chomsky and Lambek, which was about the structure of language and grammar in particular, like really structure. It was about more like logical structure. And then there is all this modern now machine learning work on meaning, which basically assigns meanings to words, but there is no real structure going on there. Like all this old stuff, like about grammar, there's no logic going on. It's like really pure statistic mostly. So how can we combine grammar and meaning? And one particular sub-problem there was, suppose you know a bunch of meanings of words. how do they together produce the meaning of the sentence, provided they are sort of grammatically well formed. And so it's something which is, of course, a practical question, but it's also an academic question, because we have dictionaries for sentences, but we don't have dictionaries for words. So how do we as humans understand a sentence we never heard before, because we do that. We regularly hear sentences we never heard before, and we know what they mean. And of course, we want to know the words inside, and then we can look on the dictionary, but it's really about the mechanism how these words together form the meaning of a sentence. And an example here is, if you hear the sentence, Royal that now rules the UK, you typically would assign Elizabeth II to it. So how do you do that? It's not just a matter of looking at these words, because there are words like royal, rules, UK. So this could actually be about sort of the rules which the royals imposed in the UK on us like peasants, or something like that. But it's really important what exactly these words are and how they interact, because if you, for example, have man bites dog and dog bites man, it are the same words, they're just swapped around, and of course they mean completely different things. And the same carries over to larger text. Like if you got a bunch of words which form sentences, and then sentences which form larger text, how can we produce the meaning of a text giving the meaning of the word? So that was a concrete question. And as it turned out, the answer was categorical quantum mechanics. Like how weird this may sound, it's not that we wanted to go mystical and said, okay, let's throw quantum mechanics at it. It was a completely accidental thing that we were in the same corridors. And I'll show you how it works and how this identification goes. So here is something. There are of course words there, like she hates Bob, but you can actually think of this as a physical process in categorical quantum mechanics. Try to explain how this works. So the things you see in the top box, you have to think of them as states of physical systems. Like she could just be a vector, Bob is a vector, hates is a vector. The fact that 3 wires come out means it's a vector of 3 systems. Like there could be 2 qubits and something else, the thick wire. So they are states of systems. This dot with 3 wires coming out, that's actually a G at Z state. In quantum, so this is notation we have for G at Z state. And then the other dot is really just a superposition. So this is a bunch of states. Now, if you look at the other part of the picture, like these are all these bent cups, you have to think of them as Bell measurements in physical terms. They really are Bell measurements. And altogether, this picture, I'll go back to the single picture, is actually a very complicated teleportation protocol, where she gets teleported in a GHZ state, and then something much more complicated is happening at the right-hand side. But you can, so these diagrams allow you to compute what happens very easily. So this is actually a diagram you can think of in physical terms. On the other hand, okay, I'm going to go back. This is a diagram you can then interpret entirely linguistically too. So like I said, the top part are vectors, but that's exactly what language people do in NLP. They represent stuff by vectors, so there is not a big change there. Okay, there are these very special things like G and Z states, which we are able to assign very, very specific meanings to. This is actually the word that, it's a relative pronoun. She, she who hates Bob. So these are way to represent relative pronouns. Now, what is the thing on the bottom? The thing on the bottom is actually something you find in textbooks on grammar, not the versions from 1950s, but something new from 2000, again by the same person, Lambeck. And he figured out that this type of diagrams is a much better representation of grammar than the things he had come up with before. So this was available. This was a theory of grammar. So just stick the vectors and the theory of grammar together, and you get this categorical grammar, quantum mechanics pictures. You just get them. Now, in the book of Lambeck, they don't think about these things as Bell effects and Bell measurements and stuff like that. They're just wires. So it's really a matter of reinterpreting them as Bell effect to actually then interpret this diagram as an actual algorithm, which takes the meaning of words and spits out of the meaning of a sentence. And I mean, I can't explain this in detail, but when you see many of these sentences, it just makes perfect sense that it works like that. It actually explains why these grammatical structures are like that. I mean, we got some attention, and the thing is, we didn't really want this thing to have anything to do with quantum. This was really a way to bring grammar and meaning together, which happened to happen in a place which we at the same time came up with to give a grammatical formalism for quantum mechanics too. But it was, well, yeah, I mean, they used vectors, and quantum mechanics uses vectors, and that was as far as we understood the connection goes. But I mean, new scientists and other places start think different about it. Like they called me a quantum linguist, and they start talking about quantum linguist and quantum mechanical words. But we really didn't want to think about it. This was really for classical NLP. That was the goal of all of this. The data agreed. These people did experiments. They outperformed every other method which was around to do certain things. I'm not going to go into details, but so as a method, this using this categorical quantum mechanics diagrams for combining meaning and grammar outperformed anything else pretty much, because nobody else had any decent framework to combine meaning and grammar anyway. Okay, now there was a problem. I mean, I was just emphasizing there's nothing quantum about it, but there was a problem, namely that if you're gonna try to stick diagrams like this, big diagrams like this, Bob gives Claire the flowers that Alice does not like, on a classical machine, it's incredibly expensive for the same reason as putting any quantum mechanical stuff on a classical computer is expensive, like we heard before, which is kind of the origin of quantum computing. Feynman said if you want to simulate a quantum system on a classical computer, it's very expensive. And similarly, just performing this model on classical computers is expensive. We did it, well, these people I just mentioned did it, but it was expensive. Okay, suddenly the world got completely obsessed with deep learning too. Like they were not interested in combining grammar and meaning, because deep learning was such a cool thing that was going to solve life, the universe, and everything, whatever. Myself, I started to write this 5,000 page book, which I just mentioned. So I actually took a little bit of distance. Book was finished. Now let's focus on the fact that this quantum native blend of grammar and meaning, because I mean, it takes quantum form, is exponentially expensive on classical hardware. Of course, why not sticking on quantum hardware? I was indicating this earlier, and Will Zhang, who's now at Goldman Sachs, who used to work at Rigetti, who used to be my student at the time. So we wrote a paper about that. We said, okay, what if we stick this stuff on a quantum computer? Do we actually get quantum advantage for algorithms? And it turned out that this was the case. So we didn't have to come up with algorithms. You could just pick algorithms which were around, closest vector problem, and do things like classification of sentences depending on their theme or sentiment or whatever you want. You get a quantum speed up if you're going to do that. I mean, we were not thinking near-term quantum computing. We were not thinking anything like that would soon happen. Well, but then Will told me, hey, I'm going to work with Rigetti and we're going to build quantum computers. So this thing is not as far away as you may think, Bob. Okay, so let's see how we can do this on a Nisky quantum computer. Like in the paper with Will, we were assuming things like QRAM, which don't exist. And in the first talk, it was said it's important to know how you actually put your stuff on a quantum computer and how you get it out. So you were considering the current situation, and something magical happened there by not having QRAM and being forced to do more tricky things like everybody has to do. Suddenly this quantum natural language stuff got a big free bonus, kind of a free lunch. I'll explain this before. So anyway, we wrote this paper, we worked out all the details of how you could actually stick this on now existing quantum computers. So I'm talking about full sentence natural language processing, not sticking two words and see whether they're closely related. Full sentence natural language processing. So sticking a bunch of sentences on a quantum computer and then asking questions. So that's what we wanted to do, question answering. We teach the quantum computer stuff, we learn some stuff from the quantum computer. Not the humongous corpora, of course, but they're full-bodied sentences and things like that which went into the machine. So we did a first experiment quite a while ago. This was on IBM Singapore. We just used 5 words and then small noun space and only 1 qubit. We made till 10 sentences. We used 5 for training and then 5 for testing, because these sentences are related. They describe a certain reality, and this is partly due to their grammatical structure that you can do that. You can give sentence meanings, and then you actually want to deduce from some given sentences other stuff that makes sense. So anyway, here are variables. We've tried some bigger stuff too, more recently on Montreal, 6 words. In particular, we used a lot more parameters to model these words. and things converge fairly okay. I mean, we can push this much harder. This is just like the recent things we have been doing, but bottom line is it works. So we get the right results because a lot of these questions are just yes, no questions we ask, and we get the right answer. So it kind of works. Let me check my time. Okay, so now why does this work, and what's so particularly attractive at this? And I got a few terms here. Quantum native, NISQ is QNLP friendly. So it's not just that this QNLP thing is NISQ friendly, it's the other way around. NISQ is QNLP friendly. So quantum native is really because we're dealing with a quantum model. I'll say a little bit later what I mean by meaning aware. Let me put some sentences underneath. So this linguistic structure, which people try to avoid because it's so expensive classically, and that's probably why they never really came up with it before us, was because it's exponentially expensive. So the natural habitat for it is a quantum computer. And you get this quantum advantage. It's very easy for several standard NLP tasks when you've done that. Now here is the big upshot. So NISQ is QNLP friendly. So how do you going to get stuff on a quantum computer? We use parameterized circuits, variational circuits. Now, variational circuit basically means you got a circuit there sitting on your quantum computer, and then you've got some gates you can play around with, but you got a circuit sitting there. And people have a word for that, which is ansatz. So you pick just some circuits, which is your ansatz, which means some meaningless assumption. And that's what you work with. Well, as a matter of fact, for us, these circuits are not a meaningless assumption. They're exactly the grammar of the sentences. So the grammar of the sentences translate in the shape of the structure. So meaning aware, what I mean by that is most natural language processing now using machine learning is very much a black box stuff. There's no way really knowing where the meanings flow and all that, while in our system, this is totally transparent. We see how the meanings flow through it. Now, okay, let me show you an example on how we get sort of a free lunch. So, wait, I'm checking my time. Okay, I'm still okay. So here we got like Alice hates Bob. This looks a little bit different than, so this is the way we encode like a sentence. We got a subject, an object, a verb, and then you got these two things. You can think of them physically as fusion operations. They have been used in measurement-based quantum computing and stuff like that. So they're standard lab stuff people do, for example, in quantum optics. So the way you have to think about this linguistically is you basically got Alice, you got Bob, and sort of gates sort of entangles them. I'm using that word now as a metaphor together. So there is now, this dot allows for Alice and Bob to now have this relation of Alice really hating Bob because Bob is always behaving badly. So this is how the linguistic diagram look. And now we can turn this into quantum circuits. Quantum circuits which will then be used in your variational circuit encoding. So basically what we do here, and this is where we use the X calculus, is it becomes something like this. So it's easier to start from here. You just take these red dots, you fuse them together and they become a plain wire. And so you got Alice connected with a dot to hates and Bob connected with a dot to hates. And that's really what you got here. And then these two outputs, if you check it, it matches. Here, this is another sentence. She who hates Bob, like we have relative pronoun here, which is this who, which is this dot. And then this actually even gives us a simpler circuit. You know, you've got a dot between she and hate. And so again, these two red dots are there, but they can fuse together. That's it. That's what you do. That's where you use this thing I earlier mentioned called the X calculus. So what the ZX calculus does is really it takes a quantum circuit and it starts treating a C0 gate as one of these green and these red dots. So see, and then you actually break it up in two primitives, a green dot world and a red dot world. And they have very simple properties, much more simple than if you want to start reasoning with C0 gates themselves. And that's why this X calculus is good for simplifying circuits in your compiler and things like that. But what it does here is it translates between linguistic structure and your quantum circuit structure. So what you do then is you're going to train your meanings of Hein and she and Bob by your training sentences. What are the meanings of this training? Like using the variational circuit paradigm. So And after you got these meanings, you can start asking questions to the machine. Like then you do your question answering. So that's what we did. So, I mean, when we were doing this, when we were doing all of this, we really were doing this with 4 people at 20% of our time, really, nothing more. But now, as of effectively yesterday, this is a team, a lot of them just started their jobs yesterday, and we're going to try to push this further. Because of all the things I was mentioning, especially here, that this is really very QNLP friendly. NISC is really QNLP friendly, especially this variational circuit paradigm, because these circuits do, so here is a story. Like if you do this classically, trying to bring in grammatical structure in your meaning, for your meaning and all that, gives an exponential blow up of the resources, because I mean, this is not a matter because we happened to use a quantum model and we happened to use the quantum tensor product for that, which of course causes this exponential blow up. It's just a matter of fact that meanings in a sentence interact intensely. Like there's all this, like an object and a subject are fed into a transitive verb. So you need this way of composing systems which a normal Cartesian product can never give you. You need something like a tensor product of which you can think really of functions. Like if you think of quantum steering, you really think of a tensor product as a function. So basically you steer the context of your object and subject in your verb. So it's expensive to make words interact grammatically. It is just very expensive. So when you go to a quantum computer, it becomes actually just in the same way as simulation of quantum system, you lose that exponential blow. But then the extra bonus is that if you now go to NISC land, where you're kind of forced to use these variational circuits for encoding stuff, I mean, that's what you have to do, that's what everybody has to do. Suddenly, these circuits give you basically a free lunch concerning grammatical structure. You just reshape these circuits as your grammar, and your grammar suddenly comes for free. There where it was exponentially expensive, now suddenly it comes for free at no cost. That's a little bit, that's why it's so promising, I think. It's also promising in general because this is a place where empirical structure, learning, and all these of course powerful techniques find structural reasoning again. And it's clear if one thinks a little bit about the psychology of people, people are not just doing like black box machine learning. It's sort of a combination of like structural learning and this sort of stuff. So I see here's a promise in this approach, not just for language, but more broader AI. Not AI in the sense of machine learning, because suddenly like the word AI sort of got like narrowed down to just one thing these days. But I mean AI in the more traditional, broader sense. I know a lot of people think like me. I know a lot of people, they think machine learning and deep learning will solve everything on its own. But in any case, there's just no way you could do anything analogous to what people are now doing in NLP, especially anything that involves more than isolated words. So that involves sentences or text. There's nothing you could do on a quantum computer now involving text, because it would be just way too expensive. Like the resources would be ridiculous. Well, we actually can already do it, especially because we get this grammar for free. I don't think I got much more to say here, except here my team again, a lot of which started yesterday. So we're starting with offices in Oxford, well, to the extent that these days we can have offices, but actually as of today, we actually got a key to offices too. So that's also something which happened today. So anyway, so this is a new branch of CQC in Oxford, and we will mainly focus on this sort of structural AI, letting structure interact with empirical and learning things. Initially, mostly for natural language, but the plan is to go beyond. Okay, that's it. Thank you.
Thanks a lot, Bob, for this really nice, insightful, and entertaining talk. So the most upvoted question is, how far from classical NLP is the QNLP?
So it's fundamentally different. I mean, that was part of the story I was saying. What we call QNLP is not just anything quantum NLP. What we call QNLP is specifically using this quantum-like, if you want, model of language, where you really have a structure to make words interact and form meaning of whole. So if you know the meaning of the words, then the structure, the wire structure, which is a bit like your teleportation and all that in quantum computing, makes these words interact and produces the meaning of a whole. Traditional NLP, they don't have these structures. They don't have these learnings. They don't have these grammatical structures. They have no way to encode it. So everything is now being learned. So one uses like huge neural networks, extreme computational power. That's of course what OpenAI is doing now with GPT-3. It's extreme computational power, while this is supposed to now actually seriously reduce the resources needed for doing NLP. Classically, it's problematic because the structure you need is exponentially expensive. On using things like these variational circuits, it just comes as part of the paradigm, the grammatical structure. And as everybody knows, it's now one of the cheaper ways to get your data on your quantum computer. So it's a nice bonus for us. So the real difference is that here there is genuine linguistic structure going on. And this is not just about sentences, this extends to entire text and things like that. So that's the key difference.
Okay, thank you very much. So big thank you again to you, Bob, as well as to all the other speakers of this session.
Okay, thank you.
This is now the end of this session on quantum computing. So on behalf of the IBM team, including Fabio and me, I'd like to thank all of you for attending this session. In 20 minutes or 15, so at 5 p.m., there will be a hands-on tutorial by James Wooten. So if you want to learn how to program a quantum computer, you can just stay in this Zoom room. And yeah, see you all later then. Bye.